Imagine a beam of light leaving the surface of a distant star. For billions of years, it travels across the darkness between galaxies. It crosses immense cosmic voids where almost nothing exists. It slips past clusters of galaxies containing trillions upon trillions of stars. It survives the birth and death of entire solar systems. It continues through an expanding universe that grows larger every second. Eventually, after a journey so vast that the human mind struggles to comprehend it, that tiny packet of light reaches Earth. Perhaps it enters a telescope. Perhaps it strikes a camera sensor. Perhaps it lands directly inside your eye. And the moment it arrives, a strange question emerges. What was that journey like for the light itself? What did the photon experience while crossing billions of years of cosmic history? What did it see? The question sounds simple, yet hidden inside it is one of the deepest mysteries in all of physics. Because according to everything modern science tells us, the answer may be far stranger than anyone expects. The photon may not have experienced anything at all. It may not have witnessed the passing of time. It may not have seen the vast distances it traveled. In a sense that feels almost impossible to understand, the entire journey may have happened instantly, not from our perspective, but from the perspective of the light itself. And that immediately raises a deeper question. What does it even mean to have a perspective? When we imagine seeing the world, we automatically place ourselves inside it. We imagine standing somewhere. We imagine occupying a position in space. We imagine moments unfolding one after another through time. Every experience you have ever had depends on this structure. You exist somewhere. You exist now. A second later, you exist again. Your life unfolds as a sequence of moments, stitched together into a continuous flow. Even your memories depend on this process. You remember yesterday because time separates yesterday from today. You imagine tomorrow because tomorrow has not happened yet. Your entire identity is built upon movement through time. Without that movement, the concept of experience itself begins to dissolve. And this is where light becomes so mysterious, because photons appear to occupy a very unusual place within the laws of nature. They move at the fastest speed possible. Nothing can travel faster. Not planets, not stars, not information, not even causality itself. The speed of light is not merely a high speed. It is a fundamental limit woven into the structure of reality. The universe appears to be built around it. And because photons always travel at this ultimate speed, they exist under rules unlike anything else we encounter in daily life. To understand why, we must first leave behind many of our everyday assumptions. When you sit quietly in a room, it feels obvious that space and time are separate things. Space is where things happen. Time is when things happen. The distinction feels natural. A chair occupies space. A clock measures time. They seem completely different. But over a century ago, this simple picture began to break apart. Scientists discovered that space and time are not separate at all. Instead, they are intertwined aspects of a single structure, a vast fabric known as spacetime. Every object moves through this fabric. Every planet, every atom, every person, every thought occurring inside your mind. Everything is moving through spacetime right now, even while sitting completely still. At first, this sounds absurd. How can you be moving if you are not moving? Yet, from the perspective of relativity, movement through time is just as real as movement through space. At this very moment, you are traveling forward through time, second by second, moment by moment. The flow feels so natural that we rarely notice it. But in a sense, much of your motion through spacetime is happening along the time dimension itself. The remarkable discovery made by Einstein was that movement through space and movement through time are connected. Increase one, and the other changes. The faster you move through space, the more unusual your relationship with time becomes. For ordinary speeds, the effect is tiny. A car traveling down a highway experiences it. An airplane experiences it. Even your own body experiences it. But the changes are so small that they are invisible to human senses. Yet as speed increases closer and closer to the speed of light, something extraordinary begins to happen. Time starts slowing down, not as an illusion, not as a trick of perception. Time itself genuinely passes more slowly. A clock moving extremely fast ticks more slowly than a clock at rest. This prediction once seemed impossible, yet it has been measured countless times. Atomic clocks carried aboard aircraft return, showing tiny differences. Satellites orbiting Earth must constantly account for relativistic effects. Modern navigation systems would fail without these corrections. The universe behaves exactly as Einstein predicted. Time is not fixed. Time is flexible. And as velocity increases, its flow changes. Now imagine continuing this process, faster and faster and faster, approaching the speed of light itself. The slowing becomes increasingly dramatic. A traveler moving at 90% the speed of light experiences time differently from those left behind. At 99%, the effect grows even stronger. At 99.9%, entire years outside might pass while only a short duration passes for the traveler. The closer one approaches light speed, the stranger reality becomes. Time stretches. Distances shrink. The structure of experience itself begins to warp. And then comes the ultimate question. What happens at the speed of light? What happens when the traveler is no longer merely approaching the limit? What happens when the traveler is light? Physics provides an answer that feels almost unbelievable. The equations suggest that the passage of time reaches zero. Not almost zero, zero. The journey that appears to take billions of years from our perspective may involve no elapsed time whatsoever from the perspective associated with the photon. This statement is so strange that generations of physicists have wrestled with its implications. Because if no time passes, what could the photon possibly experience? Experience requires duration, a beginning and an end, one moment following another. Without time, there can be no sequence. Without sequence, can there be observation? Can there be awareness? Can there be anything resembling a point of view at all? The deeper we look, the more difficult the original question becomes. Perhaps asking what a photon sees is like asking what silence hears. Perhaps the question assumes something that does not exist, and yet the mystery remains irresistible. Because photons are not rare exceptions hidden away in distant laboratories. They are everywhere. Every image you have ever seen arrived through photons. Every sunset, every face, every star, every memory connected to vision exists because light carried information into your eyes. The universe reveals itself through photons. They are the messengers connecting us to reality. And yet those messengers may inhabit a realm completely unlike our own experience. A realm where time does not flow. A realm where distance collapses. A realm where the ordinary concepts that define existence begin to lose their meaning. As we continue this journey, we will follow light deeper into that mystery. We will explore what relativity truly says about time. We will ask whether a photon can possess a perspective at all. We will discover why the universe may look radically different from the edge of light itself. And along the way, we may uncover something even more surprising. The question of what a photon sees may ultimately become a question about what time really is, and whether the flow of moments that feels so fundamental to our lives is as real as we imagine. But before we can understand the world of light, we must first understand the strange relationship between motion and time itself. Long before anyone understood relativity, time appeared simple. The sun rose, the sun set, seasons passed, people grew older. Everything seemed to move forward according to a universal cosmic clock. Whether you stood on a mountain, sailed across an ocean, or gazed at the stars from a distant continent, time appeared to flow identically for everyone. The universe seemed to possess a shared rhythm, an invisible metronome ticking uniformly throughout reality. This assumption felt so obvious that few questioned it. After all, every human experience appeared to support it. If two people synchronized their watches and later reunited, their clocks would still agree. If a candle burned for 1 hour in one room, it would burn for 1 hour in another. Time seemed absolute. Yet hidden within nature were clues suggesting something was wrong. Light behaved strangely. No matter how fast an observer moved, the speed of light always appeared the same. This simple fact sounds harmless at first, but it creates a profound problem. Imagine standing beside a road as a car drives past at 100 kilometers per hour. If another car follows behind at 50 kilometers per hour, the first car moves away from the second at only 50 kilometers per hour. Speeds add together. This feels natural. It feels unavoidable. But light refuses to obey this intuition. If you shine a flashlight while standing still, the beam travels at the speed of light. If you shine the same flashlight while riding in a spaceship traveling near the speed of light, the beam still travels at the speed of light. The universe somehow adjusts itself to preserve that speed. The question is how? Einstein realized there was only one possible answer. If the speed of light remains fixed for all observers, then space and time themselves must change. Reality compensates. The universe bends its own measurements to protect the speed of light. Lengths shrink, clocks slow down, simultaneity breaks apart. Events that appear simultaneous to one observer may occur at different times for another. This was not merely a new theory about motion, it was a new theory about reality itself. The implications were astonishing. Imagine two identical twins. One remains on Earth, while the other boards an incredibly fast spacecraft. The traveler spends years moving through space before eventually returning home. According to everyday intuition, both twins should age equally. Yet relativity predicts something different. The traveling twin returns younger, not because of biological changes, not because of unusual conditions inside the spacecraft, but because less time genuinely passed for them. Their clock recorded fewer moments. Their body experienced fewer seconds. Their entire existence moved through time differently. This prediction has become one of the most famous consequences of relativity. And although we cannot yet send humans on such extreme journeys, smaller versions of the effect have been measured countless times. Nature consistently confirms the theory. Time does not flow equally for everyone. It depends on motion. The faster you move, the slower your time progresses relative to others. At ordinary speeds, the difference is tiny. A person walking across a room experiences an almost unimaginably small amount of time dilation. An airplane experiences slightly more. A satellite experiences enough that engineers must account for it. But as velocity increases, the effect grows dramatically. Imagine a future spacecraft capable of reaching 99% of light speed. For the travelers aboard, perhaps only a few years pass. Yet when they return to Earth, decades may have elapsed. Friends would have aged. Cities would have changed. Entire generations might have come and gone. The travelers would have stepped into the future, not through science fiction, not through magic, but through the natural structure of spacetime. And the closer they moved to light speed, the more extreme the effect would become. At first, this seems like a story about clocks, a curious quirk of physics, but the deeper reality is far stranger. Because clocks do not merely measure time, they participate in time. Every physical process functions as a clock. The beating of a heart, the vibration of atoms, the firing of neurons, the decay of radioactive particles. Everything unfolds according to the passage of time. When relativity says time slows, it means all of these processes slow together. Nothing inside the moving system notices anything unusual. Life feels normal. Thoughts occur naturally. Conversations proceed as expected. A person inside the spacecraft does not feel frozen. They do not feel trapped. Their experience remains continuous. Their personal flow of time remains intact. The strange effects only become visible when comparing their journey with someone else's. And this distinction is important because it reveals something subtle about reality. There is no universal master clock. There is no cosmic authority declaring the true passage of time. Different observers experience different amounts of time between the same events. The universe permits multiple valid perspectives. Time becomes local rather than absolute. This idea alone is difficult to absorb. Human intuition evolved in a world where relativistic effects are too small to notice. everything around us moves slowly compared to light. As a result, our brains developed assumptions that work perfectly in everyday life, but fail under extreme conditions. Relativity asks us to abandon those assumptions. It asks us to accept that duration itself depends on motion. And once that idea is accepted, a new question emerges. If increasing speed slows time, what happens at the ultimate speed? Imagine gradually accelerating. Each increase brings more time dilation. Each increase causes clocks to tick more slowly relative to the outside world. The progression seems continuous, natural, predictable. But as velocity approaches the speed of light, the mathematics becomes increasingly dramatic. Time does not merely slow a little, it slows enormously, then more enormously still. The effect grows without bound, and at the limit, something extraordinary appears. The equations suggest that elapsed time collapses completely. A journey across a galaxy might require 100,000 years from our perspective. Yet for something moving at light speed, the duration associated with that journey shrinks towards zero. Not 1 second, not 1 millisecond, not 1 trillionth of a second. Zero. This conclusion feels almost impossible to visualize because our minds are built from experiences unfolding through time. Every thought requires duration. Every memory depends on sequence. Even imagination occurs moment after moment. Try to picture an existence without elapsed time, and the mind immediately encounters a paradox. What would happen first? What would happen next? The very questions stop making sense, because first and next require temporal separation. Without time, sequence disappears. Without sequence, experience itself becomes difficult to define. And here we encounter a subtle but important complication. Physicists often caution against speaking of a photon's perspective. Strictly speaking, relativity does not provide a valid reference frame moving at light speed. No observer with mass can ever reach that speed. No clock can travel alongside a photon. No physical experiment can be conducted from within such a frame. The mathematics begins to break down, and yet the temptation remains irresistible, because the limit itself hints at something profound. As observers approach light speed, time slows increasingly towards zero, and distances contract increasingly towards zero. The universe appears compressed. The journey appears shortened. The separation between departure and arrival begins to collapse. The closer one moves to light speed, the less spacetime seems to stand between origin and destination. This shrinking of distance is every bit as important as the slowing of time. Most people focus on time dilation because it feels more dramatic. But length contraction may be equally astonishing. Imagine traveling toward a distant star. From Earth, the star may lie hundreds of light years away. Yet, from the traveler's perspective, the distance itself becomes shorter. Not because the traveler imagines it, not because of an optical illusion. The geometry of spacetime genuinely changes. The destination moves closer. The universe compresses along the direction of motion. As velocity increases, that compression becomes more severe. Distances shrink. Travel becomes easier. The cosmos folds inward, and near light speed, the effect becomes extraordinary. Vast regions of space begin collapsing into something much smaller. Galaxies that seem impossibly distant from our perspective become far less separated. The architecture of the universe changes depending on how one moves through it. Space itself proves as flexible as time. This realization hints at a deeper truth. Space and time are not independent ingredients of reality. They are intertwined aspects of the same structure. Change one, and the other responds. Stretch one, and the other bends. The universe maintains a hidden balance, and light sits at the center of that balance. The speed of light is not merely a speed limit. It acts almost like a boundary between different ways of experiencing reality. Below it, time flows. Distance exists. Journeys unfold. Above it, according to everything we know, nothing can go. The limit remains absolute. And precisely at that boundary, our ordinary concepts begin to dissolve. Time approaches zero. Distance approaches zero. The separation between here and there becomes uncertain. The distinction between now and later starts to blur. the familiar framework supporting human experience weakens. We stand at the edge of a strange conceptual horizon, a place where the language of everyday life becomes inadequate, a place where asking what a photon sees may be like asking what existence looks like when stripped of duration itself. And before we can approach that mystery, we must explore another remarkable consequence of relativity. Because if time and distance can change depending on motion, then perhaps the universe does not possess a single, objective reality unfolding for everyone equally. Perhaps reality itself is more dependent on perspective than we ever imagined. At this moment, somewhere on Earth, a child is watching the sunset. Far away, another person is beginning their day. An astronaut circles the planet aboard a spacecraft. A distant star explodes in a galaxy millions of light years away. A photon leaves the surface of another star and begins a journey that may continue long after every human alive today is gone. These events feel separate. They feel organized. They feel as though they exist within a single shared present. We naturally imagine that there is a universal now spreading across the cosmos like an invisible sheet. Everything happening in the universe appears to belong either to the past, the present, or the future. This assumption is so deeply woven into human thought that most people never question it. After all, it seems obvious. Right now feels real. Yesterday feels gone. Tomorrow feels unrealized. The distinction appears self-evident. Yet relativity reveals something profoundly unsettling. The universe may not possess a universal present at all. There may be no cosmic clock declaring what is happening right now everywhere at once. And if that idea sounds strange, it is because it challenges one of the deepest intuitions we possess. To understand why, imagine standing beside a long railway track. Two bolts of lightning strike the track simultaneously, one far ahead and one far behind. You stand exactly in the middle. The flashes of light from both strikes travel toward you and arrive at the same moment. Naturally, you conclude that the lightning strikes occurred simultaneously. Now imagine another observer riding on a train moving rapidly along the track. As the train moves forward, the observer travels toward one flash and away from the other. The light from the forward strike reaches them first. The light from the rear strike arrives later. From their perspective, the events were not simultaneous. One happened before the other. Neither observer is wrong. This is the shocking conclusion. Simultaneity itself depends on motion. Events that occur at the same time for one observer may occur at different times for another. The universe does not provide a single authoritative answer. There is no absolute present shared by all observers. This discovery was one of the most revolutionary consequences of Einstein's work. Most people focus on time dilation because it sounds dramatic. Clocks slow down. Travelers age differently. These ideas are fascinating, but the collapse of absolute simultaneity may be even more profound, because it changes how we think about reality itself. If different observers disagree about what is happening now, then what exactly is the present? Where does the present exist? How far does it extend? The answers become surprisingly elusive. Imagine looking at the night sky. The stars appear scattered across a single moment. You glance upward and see them all together. Yet this is an illusion created by distance. The light reaching your eyes does not come from a single time. Every star is sending information from a different moment in history. Some starlight left a few years ago. Some departed hundreds of years ago. Some began its journey thousands, millions, or even billions of years in the past. The night sky is not a snapshot of the universe as it exists now. It is a collage of different eras, a collection of ancient messages arriving simultaneously. In a sense, every act of seeing is an act of looking into the past. Even the people around you are slightly older than they appear. The light reflecting from their faces takes a tiny amount of time to reach your eyes. The delay is microscopic, but it exists. Vision is never truly immediate. Reality always arrives with a slight lag. We live within a universe where information requires time to travel. And because light travels at a finite speed, every observer occupies a unique informational bubble. No one has access to a universal present. No one can see reality exactly as it exists everywhere at once. Instead, Each observer constructs their understanding from signals arriving through spacetime. This realization begins to blur the distinction between past and present. The farther we look, the farther back in time we see. Astronomers regularly observe galaxies whose light began traveling before Earth even existed. Some of the photons entering telescopes tonight may have started their journeys before the sun was born. These photons carry ancient stories across unimaginable distances, and they reveal something profound. The universe we observe is always historical. We never see reality directly. We see evidence of reality. We see messages sent through light. We see the past arriving in the present. But relativity pushes this insight even further. It suggests that the distinction between past, present, and future may not be as fundamental as it feels. Many physicists describe spacetime using a concept sometimes called the block universe. The idea is both elegant and unsettling. Instead of imagining reality as something continuously unfolding moment by moment, imagine the entire history of the universe existing as a single four-dimensional structure. Every event, every birth, every death, every thought, every star, every galaxy, all existing within spacetime together. From this perspective, the passage of time may not represent something physically flowing. Instead, it may emerge from how conscious beings move through the structure. Much as a person walking through a landscape encounters different locations one after another, we encounter different moments one after another. The landscape itself does not move. Only our path through it creates the sensation of progression. This picture remains controversial and deeply philosophical. Yet it arises naturally from many interpretations of relativity, and it leads to a startling possibility. Perhaps the future already exists in some sense, not predetermined in a simple way, not necessarily fixed in every detail, but existing as part of a larger space-time structure beyond our ordinary perception. The implications are difficult to absorb. Human consciousness feels immersed in becoming. We experience moments arriving and disappearing. We feel the future transforming into the present and then into memory. The flow seems undeniable, yet physics often describes a universe that appears strangely timeless beneath the surface. A universe where past, present, and future coexist within space-time. A universe where the passage of time may emerge from a perspective rather than from an objective cosmic flow. And nowhere do these questions become more intriguing than when we consider light, because photons occupy a unique position within spacetime. They connect events separated by enormous distances. They carry information across cosmic history. They weave together the fabric of cause and effect. Yet they seem untouched by the temporal separation they bridge. Consider a photon emitted by a star billions of light years away. From our perspective, the journey is almost incomprehensibly long. Entire civilizations rise and fall while the photon travels. Species evolve, continents drift, galaxies collide, cosmic history unfolds. But the mathematics of relativity suggests something remarkable. As one approaches the behavior associated with light, the temporal distance between emission and absorption shrinks toward nothing. The departure and arrival become linked in a profoundly different way. It is almost as if the photon's path through spacetime forms a direct connection between two events that we perceive as separated by vast ages. Again, physicists are careful not to describe this as a literal photon's experience, yet the implication remains deeply suggestive. The distinction between beginning and end may not mean the same thing at the speed of light. The concepts of before and after become increasingly difficult to define. And this raises a fascinating question. If the universe lacks a universal present, if simultaneity depends on perspective, and if light exists at the very boundary where our normal understanding of time begins to fail, then perhaps asking what a photon sees is not merely a question about light. Perhaps it is a question about reality itself. Perhaps the deeper mystery is not the photon. Perhaps the mystery is time, because time feels obvious only when viewed from within human experience. Outside that experience, the universe behaves very differently. Clocks disagree, distances change. Present moments lose their universality. Past and future become less distinct. The neat categories we rely upon begin to dissolve. And as they dissolve, another question emerges. Why does time seem to move in only one direction? Why do we remember the past but not the future? Why do causes precede effects? Why does the universe possess an arrow of time at all? If spacetime itself may be fundamentally timeless, where does the sensation of flow come from? The answer will lead us deeper into one of the greatest mysteries in modern physics, because understanding what a photon might experience requires first understanding why humans experience time the way we do. There is something so familiar about time that it almost disappears from our awareness. You wake up in the morning, the day unfolds, evening arrives, memories accumulate. Yesterday retreats farther into the distance while tomorrow slowly approaches. The movement feels effortless, natural, inevitable. No matter where you live, no matter what language you speak, your experience is organized around a simple assumption. Time moves forward. A broken glass falls from a table and shatters across the floor. The fragments never spontaneously leap back together. A drop of ink spreads through water. It never gathers itself back into a single droplet. A fire burns through wood. The smoke never reverses its path and reconstructs the tree. Everywhere we look, nature appears to possess a preferred direction. Events move from order toward disorder, from certainty toward uncertainty, from past toward future. And because this pattern surrounds us from birth, it feels fundamental. It feels as though the universe itself is constantly flowing forward through time. Yet when physicists examine the laws governing reality at their deepest levels, something surprising emerges. Most of those laws do not actually care about the direction of time. Imagine recording two planets orbiting each other in space. Now play the footage backward. The motion still obeys the laws of gravity. Nothing looks obviously impossible. The equations work equally well in either direction. The same is true for many fundamental processes. The mathematical descriptions of nature often make little distinction between past and future. This creates a profound mystery. If the underlying laws are largely indifferent to direction, why does our experience feel so strongly one-sided? Why does time seem to flow only forward? Why do we remember yesterday but not tomorrow? Why do causes always appear before effects? The answer may lie in one of the most important concepts in all of physics: entropy. At first glance, entropy sounds technical and abstract, but its basic idea is surprisingly simple. Entropy measures the number of possible arrangements available to a system. A neat stack of cards can be arranged in only a few specific ways. A shuffled deck can exist in an enormous number of possible configurations. The shuffled state is more probable, more disorderly, higher in entropy. This tendency appears throughout nature. Order naturally evolves into disorder because there are vastly more disordered states available than ordered ones. Imagine a sandcastle standing perfectly sculpted on a beach. Wind blows, waves crash, grains shift. Eventually, the castle disappears. The reverse almost never occurs. Random grains of sand do not spontaneously organize themselves into towers and walls, not because the laws of physics forbid it, but because the number of disordered arrangements is unimaginably larger. The universe naturally drifts toward those more probable states. This tendency is known as the second law of thermodynamics. Entropy increases, again and again, across countless physical systems. And many physicists believe this increase in entropy is what creates the arrow of time. The reason yesterday feels different from tomorrow may not be because time itself is flowing. Instead, it may be because entropy continually increases. The past contains lower entropy. The future contains higher entropy. And our minds interpret that difference as the passage of time. This idea is both elegant and unsettling, because it suggests that time's apparent direction may emerge from statistics rather than from some fundamental cosmic force. Imagine watching a glass shatter. Thousands of tiny fragments scatter across the floor. The event feels irreversible. Yet if every particle suddenly reversed its motion with perfect precision, the glass could theoretically reassemble itself. Physics allows it. The laws do not forbid it. The problem is probability. The precise arrangement required is so extraordinarily unlikely that it effectively never happens. The future appears different from the past because certain patterns are overwhelmingly more probable than others. Reality unfolds along those probabilities, and from within that unfolding, we experience the sensation of temporal flow. This perspective changes how we think about memory. Why do you remember the past? A common answer is that the past already happened, but there may be something deeper. Memories are physical records. They require structure. Neurons change. Connections form. Information becomes stored. These processes increase entropy overall. The existence of memory depends on the thermodynamic arrow of time. In a sense, your memories point toward lower entropy states. They point toward what we call the past. The future leaves no comparable records because those events have not yet contributed information to your present state. Memory itself may be deeply connected to entropy. Consciousness may be surfing along this gradient of increasing disorder. And if that is true, then our entire perception of temporal flow could emerge from the physical processes occurring within our brains. The implications are remarkable because they suggest that what feels like an objective river of time may actually arise from how information is organized within the universe. The flow feels real because our minds are embedded within systems where entropy increases. We experience the arrow from the inside. Like fish unaware of water, we rarely notice the underlying structure shaping our perception. Yet, there is another layer to the mystery. Why was entropy lower in the past? The second law explains why entropy increases, but it does not explain why the universe began in such an extraordinarily ordered state. This question leads directly back to the origin of the cosmos. When we look backward toward the early universe, we find something astonishing. The young universe appears to have possessed incredibly low entropy. Compared with the vast disorder possible today, the early cosmos was remarkably organized. In some sense, the entire arrow of time may originate from that initial condition. Everything that has happened since, the formation of stars, galaxies, planets, life, and consciousness, may ultimately trace back to that primordial state of order. The reason eggs break, the reason memories form, the reason causes precede effects, the reason time appears to move forward, all may depend on the way the universe began. And yet nobody fully understands why those initial conditions existed. It remains one of the deepest unanswered questions in science. The mystery becomes even more intriguing when we return to light. Photons occupy a peculiar position within this framework. Human experience is saturated with entropy. Bodies age, memories accumulate, physical systems evolve. Everything around us participates in the arrow of time. But photons seem strangely detached from that process. A photon emitted billions of years ago can cross the universe without aging. It carries information. It participates in physical interactions. Yet according to relativity, the duration associated with its journey behaves in a fundamentally different way than it does for massive objects. This distinction makes photons feel almost timeless, not outside physics, not supernatural, but existing at a boundary where our ordinary concepts begin to lose their grip. Consider a beam of starlight traveling toward Earth. From our perspective, the journey may span immense epochs. Civilizations rise and disappear during its voyage. Entire chapters of cosmic history unfold. Yet, the equations suggest that the separation between emission and absorption becomes increasingly compressed as one approaches the behavior associated with light. The distinction between departure and arrival grows less intuitive. The categories of before and after become harder to interpret. And here we encounter a fascinating tension. Human consciousness seems inseparable from temporal flow. Our thoughts unfold sequentially. Our experiences depend on memory. Our identities emerge through change. Everything about being human appears rooted in the arrow of time. But if photons exist at the edge where temporal duration collapses, then the very idea of a photon's experience becomes problematic. Experience requires sequence. Sequence requires time. Time requires distinction between moments. Remove those distinctions, and the concept itself begins to dissolve. Perhaps this is why asking what a photon sees feels so difficult. We instinctively imagine the photon as a tiny traveler moving through space. We picture it witnessing distant stars, crossing galaxies, and observing the universe unfold around it. But these images borrow assumptions from human experience. They assume duration. They assume perspective. They assume temporal progression. The closer we examine light, the less certain those assumptions become. And this uncertainty points toward an even deeper question. If the flow of time emerges from entropy, and if photons seem detached from ordinary temporal experience, what exactly is the relationship between light and causality itself? How does the universe preserve the distinction between cause and effect? Why can information move only in certain ways? And what role does light play in defining the structure of reality? To answer those questions, we must explore the invisible architecture connecting events across spacetime. Because light does far more than illuminate the universe. In many ways, it defines the very boundaries of what can influence what. And understanding that boundary will bring us closer than ever to the mysterious world that exists at the speed of light. Imagine standing outside on a clear night. Above you stretches a sky filled with stars. Some are relatively nearby, only a few light years away. Others belong to distant regions of the galaxy. Still others are so far away that their light began traveling long before human civilization existed. At first glance, the scene appears peaceful and simple. Tiny points of light scattered across darkness. Yet, hidden beneath that calm appearance lies an extraordinary fact. Every star you see is connected to you through a vast network of cause and effect. The photons entering your eyes are not merely illuminating distant objects. They are carrying information. They are linking events separated by enormous distances. Without those photons, the stars would be invisible to you. More importantly, they would be completely unknowable. Light is not just something we see. Light is the mechanism through which reality communicates. And once we begin thinking about light this way, something remarkable becomes apparent. The speed of light does not merely limit motion, it limits influence itself. Nothing can affect anything else faster than light. No signal, no message, no force, no information. The speed of light is woven directly into the architecture of causality. It determines which events can influence one another and which cannot. To understand why this matters, imagine that the sun suddenly vanished, not dimmed, not exploded, simply disappeared. What would happen to Earth? Our instincts might suggest that darkness would arrive immediately. After all, if the sun is gone, its light should be gone as well. But reality behaves differently. For approximately 8 minutes, nothing changes. The sky remains bright. The oceans continue orbiting normally. Life proceeds exactly as before. Only after those 8 minutes pass would Earth become aware that anything had happened. The reason is simple. Light requires time to travel. The photons reaching us now left the sun roughly 8 minutes ago. We never see the sun as it exists in the present. We see the sun as it existed in the recent past. The same principle applies throughout the universe. Everything we know arrives through delayed information. Every observation is historical. Every image is a message from another moment. In a sense, reality is always slightly older than it appears. This delay feels insignificant on everyday scales. The light from a nearby object reaches your eyes in a tiny fraction of a second. The lag is so small that it becomes invisible, but across cosmic distances, the delay becomes impossible to ignore. A galaxy 1 million light years away is seen as it existed 1 million years ago. A galaxy 1 billion light years away appears 1 billion years younger than it is today. The farther we look, the deeper into history we travel. Astronomy is not merely the study of distant objects. It is the study of ancient moments preserved in light. And this brings us to one of the most beautiful ideas in relativity, the concept of the light cone. Imagine a single event. Perhaps a star explodes somewhere in the galaxy. At the instant of the explosion, light begins expanding outward in every direction. As time passes, that expanding sphere of light grows larger and larger. Any observer reached by the expanding light can learn about the event. Any observer outside the expanding sphere remains unaware. This simple picture creates a boundary. Inside the boundary, information can travel. Outside it, information cannot. The collection of all possible paths light can take forms what physicists call a light cone. Every event in spacetime possesses one. Every moment of your life possesses one. Even the moment you are experiencing right now. The light cone divides reality into different regions. Some events can influence you, others cannot. Some future events can be influenced by your actions. Others lie forever beyond your reach. The universe is not an infinitely connected web where everything instantly affects everything else. Instead, it is structured, organized, bounded by the finite speed of light. This invisible structure determines the limits of causality itself. And once we understand this, the universe begins to look very different. Imagine two galaxies separated by an immense distance, so immense that light leaving one galaxy today will never reach the other. Not tomorrow, not in a billion years, not ever, because the expansion of the universe is carrying them apart faster than light can bridge the gap. These galaxies effectively exist beyond one another's causal horizon. Each can continue evolving indefinitely without ever influencing the other. From a human perspective, this idea feels almost impossible. We naturally imagine the universe as a single connected whole, yet relativity reveals a more subtle picture. Reality contains regions that can communicate and regions that cannot. Light determines the boundaries. Light defines the connections. Light establishes the architecture through which cause becomes effect. And this architecture becomes especially interesting when we think about photons themselves, because photons travel exactly along the edges of light cones. They move on the very boundary separating what can influence what. Massive objects always remain inside the cone. They move more slowly than light. They experience time. They age. They progress through sequences of moments. Photons are different. They travel along the edge itself, the boundary, the limit, the frontier of causality. This unique position makes light feel unlike anything else in nature. Imagine spacetime as a landscape. Every human life traces a path through that landscape. Every planet, every star, every atom, all move through spacetime along trajectories that remain within the causal structure defined by light. But photons travel precisely on the boundary. They occupy the dividing line between possible and impossible influence. And this peculiar role leads to a profound observation. Light does not merely move through spacetime. In many ways, light defines spacetime. Without the speed of light, concepts like distance and duration would lose their familiar meanings. The geometry of reality itself would change. Einstein's equations place light at the center because light determines how space and time relate to one another. It acts as a kind of cosmic conversion factor, a bridge connecting temporal intervals with spatial intervals. This is why the speed of light appears everywhere throughout relativity. Not because light is special in isolation, but because light reveals the deeper structure already present within spacetime. The more physicists studied this structure, the more they realized something extraordinary. Space and time are not the stage upon which reality unfolds. They are active participants, dynamic aspects of the universe, and light serves as the thread weaving them together. This realization carries us back to our original question: what does a photon see? By now, the question feels less straightforward than it did at the beginning. We have discovered that photons do not simply travel through an ordinary universe. They travel along the very boundaries defining causality. They connect distant events. They carry information. They establish relationships between causes and effects. Yet they seem to do so while inhabiting a realm where our usual understanding of time becomes increasingly uncertain. The closer we examine light, the more it resembles a messenger existing between worlds. On one side lies the familiar realm of clocks, aging, memory, and temporal flow. On the other lies a strange limit where elapsed time appears to vanish, a region where distance contracts, a region where ordinary intuition begins to fail. And this raises an even deeper mystery. If photons define the structure through which information travels, then what exactly is information? What is it that light is carrying across the cosmos? When a photon leaves a distant star and eventually reaches your eye, what has actually crossed the universe? Matter has not traveled from the star to you. The star remains where it is, yet something has undeniably been transmitted: knowledge, structure, pattern, information. The universe appears to be exchanging information through light continuously. Every star, every planet, every living creature, every atom. Reality itself may be far more connected to information than our everyday experience suggests. And understanding that possibility will lead us toward one of the strangest ideas in modern physics. Because the deeper we investigate light, the more it begins to blur the boundary between physical reality and information itself. By now, light has already become stranger than most of us ever imagined. What began as a simple question about what a photon sees has gradually transformed into an exploration of spacetime, causality, and the nature of reality itself. We have discovered that light defines the structure through which information travels. We have seen that time behaves differently near the speed of light. We have watched the familiar distinction between past, present, and future begin to blur. Yet, despite everything we have explored, an even deeper mystery remains hidden beneath the surface. Because photons are not only objects of relativity, they are also objects of quantum mechanics. And quantum mechanics is where our intuitions encounter some of their greatest challenges. For centuries, light seemed straightforward. It behaved like a wave. It spread outward from sources. It reflected from mirrors. It bent through lenses. It interfered with itself. The evidence appeared overwhelming. Light was clearly a wave. Then, at the beginning of the 20th century, reality delivered an unexpected surprise. Certain experiments revealed behavior that waves alone could not explain. Light sometimes acted as though it arrived in tiny discrete packets, small bundles of energy, individual units, particles. These units became known as photons. The discovery transformed physics. Light was not merely a wave, yet it was not merely a particle either. It seemed to possess characteristics of both. Depending on how it was observed, light could reveal different aspects of its nature. This strange duality remains one of the most fascinating features of the quantum world, and it immediately raises a difficult question. What exactly is a photon? The honest answer is that nobody fully knows. Physics provides extraordinarily successful mathematical descriptions of photons. We can predict their behavior with astonishing accuracy. We can build technologies based upon them. We can manipulate them in laboratories. We can use them to transmit information across continents. Yet the deeper question of what a photon truly is remains surprisingly elusive. The closer we look, the less it resembles any ordinary object. Imagine throwing a baseball. The ball follows a path. At every moment, it occupies a specific location. Even if you cannot see it, you can imagine where it is. The ball possesses a definite trajectory. Now imagine a single photon traveling through space. Quantum mechanics tells us that the situation becomes far more subtle. Before measurement, the photon cannot always be described as occupying one specific location. Instead, it exists within a cloud of possibilities, a distribution of probabilities. Not because we lack information, not because our instruments are imperfect, but because nature itself appears to operate this way. The photon behaves less like a tiny marble moving through space and more like a spread out possibility that only becomes localized when an interaction occurs. This idea is difficult to visualize because nothing in ordinary life behaves quite like it. Everyday objects appear solid, definite, predictable. Quantum entities do not. They inhabit a realm where certainty gives way to probability, where outcomes exist as possibilities before becoming realities, where observation itself plays a surprisingly important role. One of the most famous examples of this strangeness is the double-slit experiment. The setup is deceptively simple. A beam of light is directed toward a barrier containing two narrow openings. Beyond the barrier sits a screen. If light behaved purely as particles, we might expect each photon to pass through one slit or the other and produce two clusters on the screen. Instead, something remarkable happens. An interference pattern emerges. Bright and dark bands appear. The pattern resembles what we would expect from overlapping waves. Light seems to travel through both slits simultaneously. Even more astonishingly, the pattern appears even when photons are sent one at a time. A single photon seems capable of interfering with itself. It behaves as though multiple possibilities coexist until an interaction forces one outcome to emerge. For generations, this experiment has challenged our understanding of reality. Not because the mathematics fails. The mathematics works beautifully. The challenge lies in interpretation. What is actually happening between emission and detection? What does the photon do while traveling? The answer depends on whom you ask. Different interpretations of quantum mechanics offer different perspectives. Some suggest that the wave function represents physical reality. Others view it as a description of information. Some imagine branching possibilities. Others emphasize observation and measurement. Despite decades of debate, no consensus has emerged. The mystery remains. And perhaps that mystery is telling us something important. Perhaps the universe is not obligated to resemble human intuition. Perhaps reality is fundamentally stranger than the categories our minds evolved to understand. This possibility becomes especially intriguing when combined with relativity. Relativity teaches us that time and space depend on perspective. Quantum mechanics teaches us that certainty itself may be limited. Together, they reveal a universe far more subtle than classical physics ever imagined, and photons occupy the intersection of both theories. They are quantum objects moving at the speed that defines spacetime. They sit precisely where two of humanity's greatest scientific achievements meet. This unique position makes them extraordinarily valuable, not merely as particles of light, but as clues pointing toward deeper layers of reality that remain hidden from us. Consider for a moment what happens when you look at the night sky. Photons enter your eyes. Each one carries information from distant regions of the universe. Some began their journeys years ago. Others traveled for millennia. Others crossed millions or billions of years before arriving. And yet every one of those photons is also a quantum object. Each exists according to rules profoundly different from our everyday experience. The image you perceive is built from countless interactions between consciousness and quantum events. Without photons, vision would not exist. Without quantum mechanics, photons would not exist. Every sight you have ever experienced depends on these mysterious entities. In a sense, your entire visual world is a conversation with quantum reality. This realization can feel strangely intimate. We often think of quantum physics as something distant, something confined to laboratories and equations. Yet it is happening constantly. The colors around you, the stars above you, the screen in front of you, the very act of seeing, all arise from quantum processes involving photons. The mystery is not hidden far away. It surrounds us continuously. And perhaps that is one reason the question of what a photon sees remains so captivating. The photon occupies a realm inaccessible to ordinary experience, a realm where certainty dissolves into probability, a realm where classical ideas about location, motion, and observation become increasingly difficult to apply. At the same time, photons connect that realm to our own. They bridge the gap between quantum possibility and human perception. They transform distant events into visible reality. They make the universe knowable, yet they remain enigmatic. The deeper we investigate them, the more elusive they become. And this elusiveness hints at a profound possibility. Perhaps the question, what does a photon see, cannot be answered because seeing itself requires assumptions that photons do not satisfy. To see requires perspective. To possess perspective requires a sequence of moments. To possess a sequence of moments requires time. And once again, we arrive at the same mystery, waiting patiently beneath every layer of the discussion. Time, not merely clocks, not merely duration, but the very existence of before and after, the existence of experience itself. Because if a photon truly exists at the edge where elapsed time collapses, then perhaps the deeper question is not what light sees. Perhaps the deeper question is whether seeing, knowing, and experiencing can exist without time at all. And exploring that possibility will take us to the very edge of what modern physics can currently say. Because the next step in our journey leads toward one of the most profound questions ever asked. Is time truly fundamental, or could it be an illusion emerging from something deeper? For most of human history, time seemed unquestionable. Mountains eroded over time, trees grew over time, children became adults over time. Everything appeared immersed within a great cosmic river, carrying reality from the past toward the future. Time felt so obvious that few people stopped to ask what it actually was. Not how we measure it, not how clocks track it, but what time itself truly is. The question sounds deceptively simple, yet the deeper we investigate, the stranger it becomes. Because physics has achieved extraordinary success describing how time behaves, while revealing surprisingly little about what time actually is. We know that time slows near massive objects. We know that time slows at high speeds. We know that different observers can experience different amounts of elapsed time. We know that the universe possesses a history stretching back billions of years. Yet beneath all these discoveries remains an unsettling possibility. Perhaps time is not fundamental at all. Perhaps it emerges from something deeper. Imagine standing beside the ocean. Waves roll endlessly toward the shore. They seem like individual objects. You can point to them, measure them, observe them. Yet a wave is not a thing separate from the water. A wave is a pattern, an emergent phenomenon arising from the motion of countless molecules. Remove the molecules and the wave disappears. The wave is real, but it is not fundamental. Some physicists wonder whether time might be similar. Perhaps time is not a basic ingredient of reality. Perhaps it emerges from deeper structures that themselves do not contain time. This possibility sounds radical. Yet modern physics repeatedly encounters situations where time begins to lose its familiar role. One of the most important examples appears in attempts to unite quantum mechanics and gravity. Quantum mechanics governs the microscopic world. Gravity governs the large-scale structure of spacetime. Both theories are extraordinarily successful, yet combining them has proven notoriously difficult. And when researchers attempt to describe the deepest layers of reality, something surprising often occurs. Time begins disappearing from the equations. In some approaches to quantum gravity, the universe is described by mathematical structures that do not evolve through time in the ordinary sense. The equations simply exist, timelessly. This does not mean nothing happens. Rather, it suggests that our familiar experience of temporal flow may emerge from relationships hidden within a deeper framework. The idea can feel almost impossible to grasp. After all, every thought you have ever experienced unfolded through time. Every memory, every emotion, every decision. Even attempting to imagine a timeless reality seems to require temporal thinking. Our minds are products of processes occurring within time. Asking them to conceptualize a timeless foundation may be like asking a fish to imagine existence without water. Yet physics repeatedly nudges us toward that possibility. Consider again the block universe discussed earlier. Within that picture, space-time exists as a complete four-dimensional structure. Past, present, and future coexist. The sensation of temporal flow emerges from our movement through that structure. Nothing inside the block itself needs to flow. The flow exists within experience, not necessarily within the fundamental architecture. This idea often produces a peculiar emotional response. Some people find it unsettling. Others find it strangely comforting. If all moments exist within space-time, then in some sense every moment of your life remains part of reality. Childhood, adulthood, moments of joy, moments of loss. Nothing truly disappears. Each event occupies its location within the structure. The passage of time becomes less like destruction and more like perspective, like turning pages in a book whose chapters already exist. Whether this interpretation is ultimately correct remains unknown, yet it reveals how radically our understanding of time can change. And nowhere does that change become more dramatic than when we think about light, because photons constantly seem to push us toward a more timeless picture of reality. Recall what relativity suggests. As velocity approaches the speed of light, time slows. distances contract. The separation between events shrinks. The closer one moves toward light speed, the less meaningful ordinary temporal intervals become. This does not prove that time is an illusion, but it reveals that time behaves differently than our intuition expects. The thing we experience every day may not be as fundamental as it feels. Now imagine a photon emitted from a distant galaxy. Perhaps it begins its journey shortly after the formation of the Milky Way. For billions of years, it travels through expanding space. It crosses immense cosmic distances before finally entering a telescope on Earth. From our perspective, the voyage spans a substantial fraction of cosmic history. Entire epochs pass while the photon travels. Yet the relativistic structure connecting those events tells a very different story. The emission and absorption are linked by a path unlike the trajectories followed by ordinary matter. The familiar separation between beginning and end becomes increasingly difficult to interpret. The photon seems to inhabit a relationship with spacetime that challenges our ordinary notions of duration. And this leads to a fascinating question. What if the universe itself resembles that situation? What if the distinction between past and future is not fundamental? What if reality, at its deepest level, simply is? Human consciousness may then experience a sequence of moments, not because the universe flows, but because consciousness itself unfolds through informational states. The feeling of movement through time would emerge from the structure of awareness, not necessarily from an objective temporal river carrying reality forward. This possibility remains highly speculative. No experiment has definitively proven such a picture. Yet many physicists and philosophers take it seriously because modern theories keep pointing in that direction. Again and again, time appears less absolute than we once believed. Again and again, it seems more dependent on perspective, information, and relationships. And this brings us to one of the most profound insights hidden within the original question. When people ask what a photon sees, they are often imagining a tiny observer traveling through the universe, a miniature witness crossing cosmic distances. But perhaps that image is misleading. Perhaps the photon is not a traveler in the ordinary sense. Travel implies duration. Duration implies time. Time implies a sequence of experiences. And it is precisely those assumptions that begin to fail near light speed. The question may be forcing human concepts into a domain where they no longer apply, much as asking what color gravity is or what shape a thought weighs. The language itself may be inadequate. Yet this does not make the question meaningless. Quite the opposite. Its value lies in revealing the limits of our intuition. The question acts like a doorway. It begins with curiosity about light, then gradually leads us toward deeper mysteries concerning spacetime, causality, consciousness, and existence itself. In that sense, photons function almost like guides. They expose the boundaries of human understanding. They illuminate assumptions we rarely notice. They force us to reconsider what time really means. And perhaps that is why light occupies such a special place within physics, not merely because it allows us to see, but because it reveals the hidden structure beneath what we see. Every photon arriving from a distant star carries more than information about its source. It carries evidence that reality is stranger than common sense suggests. Evidence that space and time are intertwined. Evidence that simultaneity is relative. Evidence that the universe may not possess a universal present. Evidence that our ordinary experience represents only one perspective among many possible ways of describing reality. And as our journey continues, we are approaching the deepest mystery of all. Because if time may not be fundamental, then what does that imply about experience itself? Can consciousness exist without temporal flow? Can observation occur without duration? Can there be awareness in a timeless reality? These questions push us beyond physics into the borderlands where science and philosophy begin to overlap. And it is there, at the edge of what can currently be known, that we will search for the final answer to our original question. What does a photon see? There is a hidden assumption inside almost every question we ask about reality. It is so deeply embedded within human thought that we rarely notice it. The assumption is that experience requires time, not merely that experience happens in time, but that time itself is necessary for experience to exist at all. Every memory you possess depends upon temporal separation between events. Every thought unfolds through a sequence. Every sensation emerges, changes, and fades. Every emotion has a beginning, a duration, and an end. Even the act of reading these words depends on time. One sentence follows another. One idea leads to the next. Without temporal progression, the entire structure of conscious experience appears to collapse. And this creates a fascinating problem when we return to photons. Because by now, we have followed a trail that leads repeatedly toward the same conclusion. The closer we approach the behavior associated with light, the less meaningful ordinary notions of elapsed time become. Again and again, relativity pushes us toward a strange limit where duration appears to vanish. And that raises an extraordinary question. If there is no duration, can there be experience? At first glance, the answer seems obvious. Of course not. Experience requires change. Change requires sequence. Sequence requires time. Without time, there can be no observation, no awareness, no perception. The argument appears straightforward, yet the deeper we examine it, the more subtle it becomes. Consider your own consciousness. Right now, you experience yourself as a continuous observer moving through time. Yesterday feels connected to today. Today feels connected to tomorrow. There appears to be a persistent self traveling through an unfolding stream of moments. But modern neuroscience suggests that this continuity may itself be something of a construction. The brain continuously integrates information from countless sources. It assembles sensory input. It organizes memories. It predicts future outcomes. Out of these processes emerges the experience of a unified self moving through time. The continuity feels immediate and undeniable. Yet beneath the surface, the picture may be more fragmented than it appears. Some experiments suggest that the brain actually combines information across short intervals before presenting it to consciousness as a seamless experience. What feels like an instantaneous present may already contain a small temporal window. In a sense, consciousness may be stitching together moments into a coherent narrative. This does not mean the self is an illusion in any trivial sense. The experience is real. But it suggests that our perception of time may depend heavily on how information is organized. And once information enters the discussion, an intriguing possibility emerges. Perhaps experience is less fundamentally about time than it is about relationships between informational states. This idea appears in various forms throughout philosophy, neuroscience, and theoretical physics. Different thinkers approach it differently, yet many arrive at a similar intuition. What matters may not be time itself. What matters may be structure, connections, patterns, the organization of information. Imagine a book. Every page exists simultaneously. The beginning, the middle, the ending. All are present at once within the physical object. Yet a reader experiences the story sequentially. The sense of progression emerges from moving through the pages. The story contains temporal order, even though the book itself exists as a complete structure. Now imagine applying this idea to spacetime. The block universe interpretation suggests something similar. The entire structure exists. Past, present, and future all occupy their places within it. Conscious observers experience sequences because their awareness follows particular paths through the structure. Again, this picture remains philosophical as much as scientific. Yet, it highlights an important point. Experience may depend not only on time, but on how information is arranged within reality. And that brings us back to photons. Suppose we attempt to imagine a photon's experience. Immediately, we encounter difficulties. A photon possesses no brain, no memory, no biological machinery capable of awareness. Nothing in physics suggests that photons are conscious observers. The question is not whether photons think. They do not. The deeper question is whether concepts like experience even make sense in the absence of temporal duration. And here we begin approaching the limits of language itself. When humans talk about seeing, We imagine an observer existing through time. Light enters the eyes. Signals travel to the brain. Perception occurs. A sequence unfolds. Every aspect of seeing depends upon temporal processes. But if temporal separation collapses, the framework supporting the concept disappears. The photon's journey ceases to resemble a journey in the ordinary sense. Departure and arrival become linked in ways that challenge our intuitions. The distinction between before and after weakens. The idea of witnessing events along the route becomes increasingly difficult to define. In a strange way, asking what a photon sees may be like asking what a line experiences between its endpoints. The line connects them, the line relates them, but the line does not observe them. Similarly, a photon's path connects events across spacetime. It carries information. It links emission and absorption. Yet the language of observation may not apply. This realization can initially feel disappointing. After all, part of the appeal of the original question comes from imagination. We want to picture the universe from the perspective of light. We want to know what distant galaxies look like to a photon. We want to glimpse reality from the edge of spacetime itself. But perhaps the true answer is even more profound. Perhaps the impossibility of assigning a perspective to a photon reveals something fundamental about perspective itself. Perspective requires limitation. It requires a location. It requires a sequence of observations. It requires a distinction between observer and observed. Without those ingredients, perspective dissolves. And that dissolution may tell us more about ourselves than it does about light. Human beings are creatures of duration. We exist within time. Our identities depend on memory. Our hopes depend on the future. Our regrets depend on the past. The very structure of meaning in our lives emerges from temporal relationships. Remove time, and many of the concepts we care about lose their significance. Achievement, growth, learning, love, loss. All depend upon change across moments. Perhaps this is why the notion of timelessness feels both fascinating and unsettling. Part of us is attracted to it. Part of us resists it, because a truly timeless reality challenges the foundations of personal experience. Yet physics repeatedly invites us to contemplate that possibility. Not because science has proven time unreal, it has not, but because every major advance in our understanding of spacetime has made time appear less simple than it once seemed, less absolute, less universal, more dependent on relationships and perspective. The result is a universe that feels simultaneously stranger and more beautiful, a universe where photons connect distant events across billions of years, a universe where the present is not universal, a universe where clocks disagree, a universe where causality possesses a geometric structure, a universe where the flow of time itself remains an open question. And as we stand before these mysteries, another realization begins to emerge. Perhaps the goal was never to discover what a photon sees. Perhaps the goal was to understand why the question feels so compelling, because hidden within it is a longing to step outside human limitations, to see reality from beyond our ordinary perspective, to understand existence from a deeper vantage point. Photons cannot provide that perspective directly, but they can guide us toward the boundaries of our understanding, and those boundaries reveal something extraordinary. The universe is not obligated to conform to human intuition. Reality is larger, stranger, and more subtle than the stories our everyday experience tells us. The closer we approach the speed of light, the more apparent that becomes. And in the next chapter, we will follow that realization to its furthest conclusion. Because if photons do not possess a perspective, what is the closest thing the universe allows? How close can we come to understanding reality from the edge of light itself? After everything we have explored, the original question has changed. When we first asked what a photon sees, the image seemed simple enough. We imagined a tiny traveler racing through the universe. We imagined galaxies rushing past, stars streaking through darkness, and billions of years compressed into a single instant. It was an appealing picture, perhaps even a beautiful one. Yet, as we followed the implications of relativity and quantum mechanics, that image gradually began to dissolve. Photons do not appear to possess a perspective in any ordinary sense. They do not carry clocks. They do not accumulate memories. They do not observe the universe unfolding around them. The concepts required for experience seem inseparable from time, and time itself becomes increasingly problematic at the speed of light. The deeper we looked, the less meaningful the question appeared. And yet something interesting happened along the way. Although physics may deny us the ability to literally see through the eyes of a photon, it offers something almost as remarkable. It allows us to approach the edge of that perspective. Not completely, not perfectly, but closely enough to glimpse how radically different reality can become. Imagine a future civilization capable of building spacecraft far beyond anything that exists today. Not ships traveling a few kilometers per second. Not even ships reaching a small fraction of light speed. Imagine vessels capable of approaching the speed of light itself. 90%, 99%, 99.999%. Closer and closer to the ultimate limit. As the spacecraft accelerates, relativity begins transforming reality around the travelers. At first, the effects are subtle. Then they become impossible to ignore. Time aboard the ship slows relative to the outside universe. Distances contract. The stars ahead begin shifting in appearance. Light itself behaves differently. The sky changes. The universe begins to warp. And the closer the ship approaches light speed, the more dramatic the transformation becomes. The first surprise would be the compression of distance. From Earth's perspective, the nearest stars are separated by light years. The center of the Milky Way lies tens of thousands of light years away. Nearby galaxies are separated by millions of light years. The cosmos appears vast beyond imagination. Yet for travelers moving extremely close to light speed, these distances shrink, not as an illusion, not as a visual trick, but as a genuine consequence of spacetime geometry. The universe ahead contracts. Destinations move closer. The cosmic landscape folds inward. Journeys that would require tens of thousands of years, from Earth's perspective, might require only years for the travelers. The stars themselves would appear transformed. Light arriving from the direction of travel would become compressed into higher frequencies. Colors would shift. Visible light might become ultraviolet. Ultraviolet might become X-rays. The sky ahead would grow brighter and more concentrated. Meanwhile, light arriving from behind would stretch toward lower frequencies. The universe would appear distorted, focused, compressed into the direction of motion. Reality itself would seem to bend around the traveler. This phenomenon is sometimes called relativistic aberration, and it produces one of the strangest visual effects predicted by physics. Instead of seeing stars scattered evenly across the sky, an observer moving near light speed would see much of the visible universe compressed into a bright region ahead. The cosmos would appear concentrated into a glowing tunnel of light. The familiar night sky would disappear. The geometry of vision itself would change. And this transformation offers a fascinating clue. Even though we can never occupy a true photon's frame of reference, we can observe reality becoming increasingly alien as we approach the conditions associated with light. The universe gradually reveals what lies beyond ordinary intuition. Space behaves differently. Time behaves differently. Perspective behaves differently. The closer we move toward light speed, the more our familiar assumptions begin to break apart. Yet, there remains an important distinction. No matter how close the travelers approach the speed of light, they still experience time. Their clocks continue ticking. Their thoughts continue unfolding. Their consciousness remains embedded within duration. They never fully cross the boundary. They only approach it. This is one of the most profound features of relativity. The speed of light is not merely difficult to reach. It is fundamentally unreachable for objects possessing mass. Every increase in velocity requires more energy. The closer one approaches light speed, the more energy is required. The requirement grows without limit. An infinite amount of energy would be necessary to reach the speed of light itself. Nature protects the boundary. The universe permits approach but forbids arrival. And perhaps this limitation is telling us something important. Perhaps the photon's perspective remains inaccessible because it is not truly a perspective at all. Perhaps it represents a limit, where the very notion of perspective ceases to exist. Mathematics often contains such limits. Consider the horizon of a black hole. An outside observer can approach understanding it, can describe it, can calculate its properties. Yet the horizon marks a boundary beyond which ordinary intuition fails. The speed of light may represent a similar conceptual horizon, a place where familiar categories stop functioning, a place where our language begins to run out. This idea becomes even more intriguing when we consider the history of science. Again and again, humanity has discovered that reality is not arranged according to common sense. Earth is not the center of the universe. Time is not absolute. Matter is mostly empty space. Particles behave like waves. Space itself can expand. Black holes can bend the structure of reality. Every major advance has required abandoning assumptions that once felt obvious. Perhaps our intuitions about time belong in the same category. Perhaps the sensation of flowing moments captures only a local aspect of a much deeper structure. Perhaps reality itself is stranger than our temporal minds naturally perceive. Photons serve as reminders of that possibility. Every beam of starlight entering your eyes has crossed a universe governed by rules profoundly different from everyday experience. Every photon carries evidence that spacetime behaves in ways that challenge intuition. Every sunrise, every reflection, every star visible in the night sky quietly testifies to the strange architecture underlying reality. And perhaps that is the closest thing we will ever have to seeing through the eyes of light. Not a literal perspective, not a hidden viewpoint waiting to be discovered, but an understanding, a realization, a glimpse of how the universe changes as we approach the boundaries of our concepts. Because in the end, science often provides something more valuable than answers. It provides new ways of asking questions. The question of what a photon sees leads us toward deeper questions about time. Those questions lead us toward deeper questions about existence. And those questions ultimately lead us back to ourselves, to the observers standing within spacetime, wondering about the nature of the reality we inhabit. There is only one chapter remaining in our journey, one final step. Because after exploring relativity, quantum mechanics, causality, consciousness, and the possibility that time itself may not be fundamental, we are finally ready to return to the original question. What does a photon see? And what does the answer reveal about the universe and about us? We have traveled a long way from the simple question that began this journey. At first, it seemed almost playful. What does a photon see? The image arrived easily, a tiny particle of light crossing the universe, racing past stars, witnessing galaxies, traveling through billions of years of cosmic history. Yet every step we took brought us somewhere unexpected. The question was never really about photons. It was about time. It was about perspective. It was about what it means to experience reality at all. And now, standing at the end of our journey, we can finally return to that original question with a deeper understanding of why it is so difficult and so fascinating. The first thing we discovered is that light occupies a unique place within the structure of the universe. Nothing moves faster. Nothing carries information beyond it. The speed of light is not simply a property of photons. It is woven into the geometry of spacetime itself. It defines causality. It determines which events can influence one another. It establishes the framework within which reality unfolds. In a profound sense, light does not merely travel through spacetime. It helps define spacetime. And because photons move at this ultimate speed, they exist at a boundary, unlike anything encountered in everyday life. As objects move faster and faster, time slows relative to the outside universe. Distances contract. The separation between events shrinks. The familiar structure of experience begins to change. And at the limit represented by light, the mathematics of relativity points towards something extraordinary. The elapsed time associated with a photon's path collapses towards zero. Again, physicists are careful with this statement. Strictly speaking, there is no valid inertial frame moving alongside a photon. Relativity does not allow us to simply step into the shoes of light and look around. The concept itself breaks down, yet the limit remains revealing. As we approach the conditions associated with light, The distinction between departure and arrival becomes increasingly compressed. The journey appears shorter. The duration appears smaller. The universe behaves in ways that challenge our deepest intuitions. And this is where we arrive at perhaps the most honest answer science can currently offer. A photon does not appear to see anything, at least not in the way humans understand seeing. Seeing requires an observer. An observer requires a sequence of experiences. A sequence requires time. Without temporal progression, the entire framework supporting observation disappears. The question itself assumes concepts that may not apply. In that sense, asking what a photon sees may be like asking what a shadow remembers or what a number dreams. The language points beyond the domain where it remains meaningful. Yet paradoxically, the failure of the question teaches us something profound. It reveals how deeply our understanding of reality depends upon time. Everything we call experience unfolds within duration. Every thought, every memory, every hope, every fear, every act of perception. Human existence is inseparable from temporal flow. We are creatures of before and after, creatures of beginnings and endings, creatures whose identities emerge from change. And because of this, it is extraordinarily difficult for us to imagine a reality where those distinctions disappear. But physics repeatedly suggests that reality may be larger than our intuitions. The universe does not appear obligated to organize itself according to human expectations. Again and again, science has revealed deeper structures hidden beneath ordinary experience. Earth is not stationary. Space is not empty. Time is not absolute. Matter is not solid. Particles are not always particles. Reality continually turns out to be stranger than it first appears. And photons stand at the center of many of those discoveries. Every beam of light arriving from a distant star carries more than information about its source. It carries evidence. Evidence that spacetime is flexible. Evidence that simultaneity is relative. Evidence that the present is not universal. Evidence that distance and duration depend on perspective. Evidence that the world revealed by common sense is only part of a much deeper story. In this way, photons become something more than particles. They become guides, messengers from the hidden architecture of reality. Every sunrise, every reflection, every color, every star in the night sky. Each reminds us that the universe operates according to principles far more subtle than our everyday experience suggests. And perhaps nowhere is that subtlety more apparent than in the mystery of time itself. Because after more than a century of relativity, quantum mechanics, and modern cosmology, one remarkable fact remains. We still do not fully understand what time is. We know how to measure it. We know how it behaves. We know how it stretches and contracts. We know how it interacts with gravity and motion. Yet, its fundamental nature remains elusive. Some theories suggest time may emerge from deeper relationships. Others suggest it may be woven into the foundation of reality. Some imply that past, present, and future coexist within spacetime. Others point toward entirely new possibilities not yet understood. The mystery remains open, and perhaps that openness is part of what makes the universe so endlessly fascinating. There is a temptation to think that science gradually removes mystery from the world, that every discovery replaces wonder with explanation. But the history of physics tells a different story. Every answer reveals deeper questions. Every discovery opens new horizons. The more we learn, the more extraordinary reality becomes. The photon is a perfect example. What once seemed like a simple particle has become a gateway into questions about spacetime, causality, quantum mechanics, consciousness, and existence itself. The deeper we look, the more profound the mystery becomes. And perhaps that is the final lesson hidden inside the original question. Sometimes, the most important questions are not valuable because they have answers. They are valuable because they change the way we see. The question, what does a photon see, invites us to step beyond ordinary intuition. It encourages us to imagine reality from outside the perspective we normally inhabit. It reminds us that the universe is far larger than our everyday experience. And in doing so, it reveals something beautiful. For all our technology, all our equations, all our telescopes and particle accelerators, we are still explorers, still standing beneath the stars, still asking questions, still trying to understand what kind of universe we have found ourselves in. Tonight, somewhere beyond the reach of the naked eye, countless photons are crossing the darkness between galaxies. Some began their journeys before Earth existed. Some will continue long after humanity is gone. They travel silently through the vast architecture of spacetime, connecting distant events across the cosmos. They carry ancient stories written in light, and although they may never experience those journeys in any human sense, they allow us to experience them. They allow us to see farther than our ancestors ever imagined. They allow us to glimpse the hidden structure of reality itself. And perhaps that is enough. Perhaps the greatest wonder is not what a photon sees. Perhaps the greatest wonder is that through light, the universe becomes capable of seeing itself. As always, thank you for joining this journey into the deeper mysteries of reality. If you enjoyed this exploration, consider subscribing to Science Sleep Theory for more calm, reflective journeys through physics, cosmology, and the hidden questions woven into the fabric of existence. Until next time, rest well, stay curious, and let the universe remain wonderfully mysterious.